Today I'll be going over section 1.1, which is just going to be some definitions and some terminology. Okay, so when you're talking about differential equations, okay, we talk about the derivative. Okay, and we should know from, calculus dy dx is a representative of the derivative of the function y in terms of x, or we see it as y prime, or we could see f prime of x. So what you would get in this course would be some type of differential. Let's say 3x squared y, and what our goal is going to be is, what is a function that we could that can be represented by y. Okay, so really that's the key question that we could have here in this course, is you'll be giving some type of differential equation. Okay, and our goal is to find out, well, what is y, or what functions could be representative of y, or what do these functions look like. So for example, let's say that y was e to the x cubed, and then you could see if you took the derivative, we would get 3x squared e to the x cubed just by using chain rule. And then you could see that it matches. But again, there's going to be different methods of doing that, even though maybe some of you could see that quickly, right? That would be the function that we could use for y in this situation, okay? But remember, you could also have another function, plus 2, e to the x cubed plus pi, and so on. So we know what these functions would look like, right? They would have some form of e to the x cubed plus c, meaning that this is just a general form. This is not a particular equation for this differential, okay? So any differential equation, right, the definition, okay, is an equation containing the derivative, spelling, of one or more functions. All right. Okay, so you could have different types of differential equations. Okay, and one is an ordinary differential equation. The book, or the ebook, will use ODE, okay, for ordinary, and this can contain more than one unknown function. All right, so you could have here we could have dy over dx plus y equals e to the x. Here you have only one unknown function would be y, right? And then here you could have say the second derivative with respect to x of y plus the first derivative plus say 2 times y equals 0. So there you can have, they have only one unknown function, but you could find, we could look for the first and second derivative, but you could also have something like this, dx, so the derivative of x with respect to t, plus the derivative of, say, y with respect to t, equals some function 2x plus y, where you have, if you notice, two different functions. You have x and you have y, right? So y and x. So there you would have two different functions, and they're looking at respect to time instead of x. Okay, so that's an ordinary, right? And then the other one is your partial derivatives. Okay, so you'll have a partial differential equation, or PDE, not PEDs like Mark McGuire. And this is, just notice the notation, right? You have the partial, right? Say a partial second derivative, right? The way you have that little, just exaggerate it, the D, right? Or delta, I guess. Maybe that's a delta, I'm not sure. If you guys know, you could bother me and say I'm wrong with all these things. All right, but here you could see you have the notation with the partials. So just, you know, your partial PDE, we don't see too much in the beginning of the course, but you will see the ordinary differential equations over and over again. So those are the different types. And then we have order. Okay, so order, you could just think of what derivative it is, kind of like degree in a sense. I didn't want to make it a partial, get in the habit of doing that. I just want to do like second derivative, right? Say plus 6 times first derivative equals some function here. So order, this would be a second order differential equation. Okay, because it has the second derivative, like it's in that order. You know, you could have whatever the nth, say it's like the nth derivative, right, plus, let's say, minus 1. Something like that, say, and this would have nth order. So pretty straightforward for order. A first order, though, let's just go to here, can be written in this form where you have some function of xy dx plus n, which is some function of xy dy equals 0. So you could see that, you know, first order could be written in a different form, and then you could rearrange it and get it to look like the first order. But again, because it's written that way, right, get rid of the dx, move a couple functions, you still have it in the form of some function dy dx, right? Say we go like that, equals, you could do something like this. Okay, and then you still have your first order would be some function that looked like this, right? Remember, m and n are just functions of x and y, so you could still get it into that first order look. All right, and then forms, right? You could just see there are different ways of looking at things. Okay, so what we did up here, right? This is a differential form. Right, so that's a differential form. Okay, normal forms though. Differential form, normal would be, you know, what we were looking at, dy over dx equals a function of xy. Okay, you have your second derivative will equal some function of x, y, and the first derivative. And then this continues, like if it was the nth derivative, right? It would be some function of x, y, and then the n minus 1th derivative. Actually, we could do it this, rewrite it this way. First, and then all of the ones up to the n minus 1th derivative, like that. So that's a normal look, okay? And then the next thing that we want to talk about is if it is linear or linearity. Okay, so in linearity, right, the look is, let's say you have some function, your nth derivative plus some function of x. So remember, these are all functions of x times derivatives. Okay, so times derivative. So this is n minus 1th derivative and so on, right? So we could go down to the first derivative and then some function, g of x, right? You know, f of x, anything a function of x at the end. So for example, what you would see is, let's see, an example could be, we could have like 5x second derivative plus 2x first derivative plus y equals, say, e to the x. That would be an example that you would get. Okay, so like we're just, you know, if you're looking at, say, a first order, you would have some function times the first derivative plus some function times the original function, and then it doesn't really matter the look of it, but you would have then equals some function of x. I mean, again, over here, oops, I didn't even catch that. So just remember, you always have a chance that your function will be in there as well, like the y function, not the derivative, the y function, and then minus or plus some function of x equals 0, and then you can see, you know, how it matches up that way. But remember, like your linearity, what you want to look for is you have all types of derivatives of your function y. Everything else, right, is a function of x, Okay, so it looks like that. Oh, yeah, even, right? So don't forget there could be a function of x in front of y as well. So a sub 0 of x times y, like that. So again, all functions of x. That little mistake will help you. Okay, so another example could be, let's say we're doing a second derivative problem. You would have, say you had 2x squared, y second derivative, plus x, y first derivative, right, plus 2y, right, equals, say, cosine x. Something like that would be linear. Okay. So let me show you what is not linear. Non-linear would look like, say you had 1 minus y times y second derivative, right? Say you had something like that, plus 2y equals 0. Non-linear, right? Because this is not a function of x, okay? If you have a second derivative plus cosine y equals 0, again, not a function of x, okay? And then, so say it's the third derivative plus the second derivative plus y squared equals 0. Still not a function of x, okay? So you're just seeing y prime. Those are the only things you want to see, is like a y prime, and so on to the nth derivative for it to be linear. All right. And the last thing in this section is just showing solutions to a problem like I was doing earlier. So basically like verifying a solution. Okay, so if you had y double prime minus 2y prime plus y equals 0, right? And let's say we want to verify that y is equal to e to the x times x, or x e to the x. So what you want to do here is first find your derivatives, y prime, right? Remember product rule, so derivative of x is 1, so it's e to the x plus x e to the x. Remember, derivative of e to the x is e to the x. And then the second derivative would be e to the x plus e to the x plus x e to the x, or 2e to the x plus x e to the x. And then what we want to do is just do our substitutions, right, for y prime and y double prime. So here you would have 2e to the x plus x e to the x, right? And I'm just starting with the left side. So left side you could say equals, and then minus 2 times the first derivative, e to the x, plus x e to the x, and then plus function, and then we could say, right, simplify it down, you get 2e to the x plus 2x e to the x minus 2e to the x plus minus okay, you can see everything cancels and we get 0, and then that equals the right side. Okay, and then you can see how that verifies. All right. I mean, a couple things. This works if you look at, like, going back to domain of your function, right? So this could be on the interval, right? Negative infinity to infinity. Just want to show you you know, because sometimes let's see. Just want to give you one example that you would see on your homework. Yeah, so let's say you had something like this, right? And they're giving you y to be 1 over 25 minus x squared. Okay, so here what you would have is, let's find the first derivative. So remember, if you're a little confused, we could rewrite this by bringing it up and putting -1. You could do a quotient rule, very annoying quotient rule, but I like chain rule, bring that up. You know, it's -1, 25 minus x squared to the -2 times derivative of the inside, which is -2x, right? Okay, so that gives us 2x, right, positive over 25 minus x squared, the whole thing squared, right? So then, here we know y prime we found, so this was the left side. This was the left side, and then we could do, like, what would 2x times y squared, so we could just write it 2x 1 over 25 minus x squared, the whole thing squared, which, I mean, that's pretty easy, because that's just 1 squared is 1, so times 2x you get 2x, and then we could just write this as squared in the denominator, and this is equal to the right side. Why do I keep writing? Okay, so left side's equal to the right side. So we verify that that is true. When you see a function like this, think about your domain, okay, of this function. So, you know, here, to see what intervals that you could come up with here, you're really just looking for the domain, right, of our function y would be everything but 5 and -5. So you would have it written, you know, like set notation, -infinity to -5, and then you would have -5 to +5, and then 5 to infinity. And just remember, you're using parentheses here. We don't want to include 5 or -5, okay? And then you could see, like, on specific intervals depending on what the constant is. So this could be a function, but what if we added 3 to that function? If it was like 1 over 25 minus x squared plus 7, right? Say, for example, that would still give you the same value, but now it's moving your graph up, so it might only be in one of these specific intervals that we're talking about. Okay, so that's 1, 1.